Okay, in this video, we're going to talk about this question for the entirety of the video. We've got a right angle triangle, we've got, that's outlined in red. Now that right angle triangle is a block of material with a refractive index of 1.5, as you can see from the diagram. The black ray represents a ray of light that comes into the block and gets refracted and then approaches that the second boundary of the other side of the triangle at an angle of 52 degrees to the normal. So the questions are as they stand here. Determine what theta is, and that is the angle to the normal of the incident ray coming into the block. And where and at what angle does the ray emerge from the block? What I would say is that if you're feeling pretty confident with some of the video stuff we've had before, have a go at this, these questions and see if you can get the answers that we get at the end without too much difficulty. And obviously just check your answers up. If you get them wrong, then feel free to go back through, or if you're not feeling confident, do watch through as we go as well. Okay, so in order to determine theta, we need to utilise Snell's law. That's what we've got to use here. So Snell's law is n1 sine theta 1 is equal to n2 sine theta 2. Now we need to identify what all these terms are. All these terms represent different things in this question. So theta 1 is what we're going to be looking for. That's that value right there. So that's what we're looking for. N1, on the other hand, is going to be A. You can assume that this is A. You've not been told anything else. You've not been told it's been put in anything. So that's going to have, N1 is going to be 1 sine theta 1. That's what we're looking to find out. Is equal to N2 sine theta 2. N2 is going to be our refractive index here, 1.5. Times by sine of theta 2. Well, we've got a bit of a problem now because this angle here is theta 2. And we don't know what theta 2 is. Or do we? Well, if we look at the geometry of this situation very, very carefully, what you'll notice is that this line is directly parallel to this line right here. Which means, given the geometry of the situation, we can suggest that this angle right here, my blue pen, this angle right here is 52 degrees as well as this one right here. That means this one is 38 degrees because from a perpendicular line, because the normal line is 90 degrees, therefore 90 minus 52 would give us 38 degrees for theta 2. So that's quite nice because that means we can then throw in the value of sine 38. So, what can we do with this equation? Well, we can get rid of a few terms. First of all, we need to get rid of this 1. We can get rid of this 1 by dividing both sides by 1. So divide both sides by 1, we get rid of the 1, because anything divided by 1 is itself. Then we end up with theta on its own. Obviously, to find an angle as part of a sine function is you go theta 1 will be equal to sine to the minus 1 of 1.5 times by sine 38 in this case. And when we work all that out, so times sine of 38, we get an answer of 67.44. So, well done if you get that answer without my help. Right, the next question is a little bit more complex because we need to then look at more geometry of this situation. Well, interestingly enough, what we can see from this situation is that we've got an angle here that's at 34 degrees. We've got an angle here that's 52. So we're being told something about the triangle that is obviously important for some reason. First of all, we need to make a decision. Is this ray going to emerge here, or is it going to be totally internally reflected because the angle of incidence is greater than the critical angle? Well, in order to know that, we need to know what the critical angle for this box to air boundary is. So, what we can do is we can suggest, okay, well, I need to know what the critical angle is for light coming from this block into that. Now, the equation for that will be 1 over sine C is equal to n. Where n, you'll remember from the explanation of where this equation comes from, is n1. That's the material that it's coming from. So, what we've got here, we can rearrange this equation for sine C, or for C. So C is going to be equal to sine to the minus 1 of 1 over n. And when we work that out, 1 divided by 1.5, sine to the minus 1 of that answer, gives us 41.8, or for the most part, 42 degrees. Okay, so the critical angle for this shape, or for this boundary from there to there, is 42 degrees. So ask yourself, do you know whether it's going to totally internally reflect or not? If you're not sure of the answer, I would recommend going back and looking at one of the previous videos about total internal reflection and critical angles. So, those of you who have worked out what happens next, yeah, 42 degrees is the critical angle. This angle is greater than 42 degrees, so yeah, we can quite happily suggest that this is going to reflect, in that direction. Okay, so it's going to reflect off in that direction, which means that we are going to expect that there is another boundary involved here. Now, interestingly enough, there is even more geometry we can do here, because effectively we're now at a Snell's law problem. We need to know what this angle is right here. Because if we know what that angle is right there, we can work out what this angle is going to be right there. We are expecting that it probably will refract out at this point, because the angle looks fairly tiny from the geometry, but when we work out this angle, we'll determine whether or not it will totally internally reflect at this point here. I've got a little bit of a hint for you. I made up this question, so I kind of know that it's not going to totally internally reflect, but we can prove that as well. So, what you'll see here is we've got one big triangle right there. Okay, so, interestingly enough, what other angles can we work out from this situation? Well, the ray is being reflected at this point right here. When rays are reflected, as you may or may not know from GCSE, that you get the angle of incidence will equal the angle of reflection. So that angle is also going to be 52 degrees. If that angle is 52 degrees, look very carefully, we've got 52 degrees, and remember from the normal line to the surface of the boundary, it's 90 degrees. So the angle in here is 38. Well, if you look very carefully now, we can actually see, I'll draw a dotted line around it, a triangle of its own right. We have two angles of the triangle, So therefore, you could potentially tell me what that angle is between the ray and this horizontal part of the triangle is. Well, if you've got 34 and 38, that means you've got 60, 70, 72. So you've got a total of 72 degrees. So 72 degrees. How many degrees is in a triangle? You've got 180. So what's missing from this calculation? Well, we've got 180 degrees is, so we've got 17, we've got 108. So we've got 108 degrees. If we've got 108 degrees in that entire angle right there, and we know that this bit is 90, we can take 90 off that. What does that leave us with? That leaves us with 18 degrees. So that means that this angle, the angle we were looking for, I'll draw it in a different colour just to make it nice and clear. This angle right here is 18 degrees. So we're now into our Snell's law calculation. We know it's not totally internally reflecting. Why? Well, because we know the critical angle between this material and air is 42 degrees. 18 is less than 42, so it's not going to totally internally reflect. It's going to refract. So at this stage, we can rub out our calculation at the top here. I want to use that space for up the top at the top here. So we're back into Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. We need to then put all the numbers in that we know. So N1 in this case is going to be 1.5 sine of this angle right here, which is 18 degrees, is going to be equal to N2, which is going to be 1 sine theta 2. We don't know what theta 2 is. So that's what we're looking to find out. So again, we can get rid of the 1's because we're dividing both sides by 1 to get rid of it. That means that we end up with a calculation of sine to the minus 1, 1.5 times sine of 18. So 1.5. That gives us a refracted angle of 27.6 or 28 degrees. So that's telling us that this angle here is 28 degrees. So in answer to this question, what we're suggesting here is that we've determined theta 67.4 degrees. We've determined what the angle and where it's being refracted from. So it's emerging from the baseline of the triangle, and it is refracting at an angle of 28 degrees to the normal. So a fairly complex problem, but it all relies on your knowledge of geometry and being able to see around the fact that triangles have 180 degrees in them. Can you work out what two of the angles are? If you can, then you can then use that information to work out what a third angle is in this case. And you're relying upon the fact that the angle to the normal line is at 90 degrees to the surface, and that is going to be a permanent feature. And like I said, you can use all of those to help you to work out these values. So for those of you who skipped to the end of the video, you'll be able to see the answers here. You'll be able to see that it refracts out of the bottom at 28 degrees and that the initial angle is 67.4 degrees right there. So we've utilised the critical angle to see where it would go. We know it doesn't refract out here because it's greater than the critical angle. Then we worked out how it actually comes out of the material and where as well. Okay, so fairly complex problem. Have a go, have a look through that. If there's any questions, write them down and we'll get back to it in your own time.